Hello everyone, welcome to the second part of this Indian Olympiad Qualifier exams in chemistry. We are talking about question paper code number 31. We have had discussion about the questions in organic. In the second part, we are going to take about discussion about the questions in inorganic chemistry. And starting with the part 1 of this section 1, A1, where single option correct questions are there. So we have got the very first question. This is on the coordination compounds, and crystal field theory was the subtopic on which this question was based on. We are given some of the complexes and we are asked about the order of the CFSE, which is crystal field stabilization energy. Here we will be having some factors which affect crystal field stabilization energy. Based on that, we can compare. The answer to this question would be coming as A. Finally, we'll see in our detailed explanation. So what things we should be keeping in mind when we are going for this answer? First thing is CFSE depends on the identity of the central metal atom. This has got much more dominating effect on the values of the crystal field stabilization energy. So as we are moving from some central atom, which is from 3D elements, starting from scandium through zinc, when you are going to the 4D transition series, where the electrons are filled in the 4D, the value of the crystal field stabilization energy for the same oxidation number and with the same ligand is found to increase. And again, going from 4D to 5D, this is going to increase even further. First point. Second point is this also depends upon the oxidation number of the central metal atom, because if there is the higher oxidation number of the central metal atom, this can attract the ligands much more strongly, and stronger the attractive forces, closer this will be going to the d orbitals of the metal, greater will be the crystal field splitting. That non-degeneracy of the d orbitals is being lifted much more in much more way, greater difference of energy is going to be. Number of ligands also modifies the value of the CFSE, because if you are having 6 coordination number, you have got greater value of the CFSE in comparison to coordination number 4. We have put our star here, star mark, which is basically when we are saying this 4, this should be tetrahedral, because if this is square planar complex, then the overall splitting is found to be much greater in comparison to basically the difference between EG and T2G set of orbitals is going to be quite higher in square planar, so that we have to be a little bit careful about. Also, there is very dominant effect, that is the ligand. Not dominant actually, we should say that is more versatile thing, where we'll be finding variety of the questions on which the ligands are being changed, and we are asked for what is the value of the crystal field stabilization energy. Although this thing is not going to be operational, so we have shown this with the little bit faded colors. Here we have got all the ligands as ammonia and all the complexes, so that is not going to be a deciding factor. We'll see here, first of all, what is the crystal field stabilization energy. So we are going to say, the idea of the crystal field stabilization energy is, if you have taken one isolated metal atom, some central metal atom, and you are bringing it in influence of some of these ligands, then how much stabilization is brought about by those ligands when we are having this metal present in some field of these ligands. So we are taking the example of some octahedral complex, which is going to have the electronic configuration as T2G1. So there is only one electron basically in the D-shaped shell. We'll see how these electrons are filled. So that is the energy coordinate on the y-axis. And here we have got T2G set of orbital. And in this T2G set of orbital, we have got just one electron present. We can fill that electron in any of these orbitals. These are all having same energy. We say these are degenerate orbitals. So one electron is present here. Now, the splitting between these two, what we call as delta O, sometimes we write this as dq. This is basically delta is written as in the terms of 10 dqs. So this set of orbital, which is called as T2G, is lower orbital. This set is higher orbital, higher energy orbital, that is EG set of orbital. E and G are some spectroscopic terms. We at 10 plus 2 level are not doing this in our curriculum. So this orbital which is going lower in energy, that has been basically stabilized. This is going to be stabilized by effect at 0.4 times delta O. This delta O was the overall splitting from the highest to the lowest. The other two orbitals which are going higher in energy coordinate, their energies are being increased by plus 0.6 times delta O. And the center with respect to which we are considering, this center with respect to which we are saying this is becoming stabilized or destabilized, is called as barycenter. So in comparison to barycenter, which is hypothetical energy level of these d orbitals, some of the orbitals are getting lower energy coordinate, some of the orbitals are getting higher energy coordinate. Now, depending upon how many electrons we are filling, overall there will be some stabilization possible because of this T2G electrons. If the T2G orbitals are being filled, we'll be getting stabilization. So here we see how we are going to do the calculation of the this CFSE. The formula we are going to use is the number of electrons which are going into T2G, they are going to be stabilized. So we are going to write the number of electrons in Tg multiplied by minus 4 points delta O. And the electrons which are going into this higher energy coordinate, here they are going to bring in destabilization. So the number of electrons in each set of orbitals multiplied by 0.6 times delta O. Also, there is one term which we are not using over here, that is the pairing energy. So when there will be electrons paired up, like if there was some this kind of situation in some of the electronic configuration, then there will be some electron-electron repulsion coming into that we are calling as pairing energy. Here this is functional in our given T2G1 case, so we are skipping that. So we are now writing this thing. So this is going to be stabilization coming in, and there is no electron in high energy orbital. So this is basically destabilization. The number of electrons changing, we can calculate the CFSE accordingly, right? So this stabilization basically is with respect to the barycenter, and negative sign will be telling us that our complex has been stabilized. We will be getting the values of CFSE either 0 or negative. Positive values will possibly not be there. We cannot comprehend that. Okay, so coming back to our these options, what we had in this given question. What we see, we can observe over here, all ligands are ammonia, so ligand effect is going to be irrelevant. We talked about that already. Then we have got zinc. This is going to have tetrahedral ligand, and there are going to be 4 ligands. So this is going to have the least value of the CFSE because the 4 number of ligands tetrahedral is having smaller value of delta. Now, iridium is going to be from the 4D transition series. This is going to have higher value of the CFSE in comparison to cobalt when they are in the same oxidation states. So in comparison to cobalt, iridium is going to have higher value. Iridium we can say is going to have highest CFSE, and our zinc is going to have the least CFSE. So now we have to compare between these two things. How we can compare? There is a difference in the oxidation state. Here we have got +2 oxidation state. Here we have got +3 oxidation state. So +3 oxidation state is going to have greater value of the CFSE. That's how we have decided our answer was going to be A, in which the iridium was having the highest value, zinc was having the least value, cobalt 3+ was having greater value in comparison to cobalt 2+. That is how we can compare the value of CFSE in that given case. I hope that was clear to all of you. Now we are going to take the next example, the next question. This question was about the transition element, where we have got the value. We have to understand what is the nature, what is the reason behind the colors of these compounds which we are getting. So the reason for the colors of these compounds, we were asked, there was one option, there is a charge transfer, and there is another option which was the DT transition. So this charge transfer versus DT transitions we have to compare. Answer in this case is coming out to be the charge transfer. We'll see how that is happening. So the thing is, when we have got D1 to D9 configuration, like at least there is 1 electron present in D subshell, or at least there are, or maximum D9 electrons are present, then we can have DT transitions possible, because then only electronic excitation can be taking place. So for most of the transition elements, we see this is happening. This is our lower energy state. This can be depending upon tetrahedral octahedral complexes. In tetrahedral or octahedral, this can be changing. This should have been written the other way around, T2G, and this would have been EG. This would have been E or T2, like that. First one was for tetrahedral, the second one is for the octahedral. So depending upon the cases, when the electrons are present in lower energy state, the excitation from the visible radiation can be made possible because the difference is not very much high. Electron can be excited into the higher energy level, and this excitation is associated with this color change, and this excitation is taking place from one set of d orbital to another set of d orbital. That's why we are calling this as DD transition. Okay, in this DD transition, at least one electron or maximum 9 electrons can be given this possibility, because if there are 10 electrons, we'll be having those quantum mechanical restrictions like Pauli exclusion principle. We cannot excite electron in the higher energy level. That will not be possible basically. So whenever we have got D0 or D9 configurations, this thing is what we have seen over here. This thing is going to be non-operational. This thing cannot be possible. Then there is the possibility in such cases that we can have charge transfer spectra. There also electronic excitations are taking place, but there we have to keep into mind that electrons can be going from one molecular orbital to the another molecular orbital. That can be understood from the molecular orbital perspective. And although we don't do it in molecular orbital theory at this particular level, 10+2 level, so we can try thinking that there are certain orbitals, the orbitals which can be written the way we have been writing for the homonuclear diatomic molecule for the second period. That way we can write the atomic or the molecular orbitals for these coordination complexes as well. We won't have that detailed discussion, but we'll be having an idea how those molecular orbitals are formed and how those electronic transitions are taking place, which we are calling as the charge transfer spectrum. This charge transfer, how it is, we'll be seeing here. This is a typical diagram for the ligands when they are being formed. These are the d orbital energy of the d orbitals of the metal, and here are the energies of the d orbitals of the ligand. Ligands can be forming sigma bonds, ligands can be forming pi bonds, and at the same time there can be ligand having empty pi star molecular orbitals present as well. Metal can also have some of the orbitals, like this can be the low lying orbital, this can be higher energy orbital. So depending upon the identity of the metal and the ligand, it can be possible that some of these energy levels can be populated. Say these energy levels are populated, these energy levels can also be populated, or the other way around. This kind of situation can be there. Assuming we are having some this kind of state, we have got some this kind of situation. Now we can have electronic transitions possible in two different ways. One is ligand to metal, that we call as LMCT, ligand to metal charge transfer. Another one is we call as MLCT, which is metal to ligand. So it depends on from which orbital electrons are going into which kind of orbital. So when electrons are going from lower to higher, that excitation is again taking place just like it was happening in the DD transition. So here also the filled molecular orbital electrons are being excited into next available empty orbitals. That is the reason of this DD transition, and that is ultimately the reason of the color. The thing is, this transition is going to take place with a relatively smaller amount of energy possible, that is lying somewhere in the visible region. And that is why we can see the color, because visible region is the only thing what our eyes can observe, our brain can comprehend. And these kind of transitions are basically allowed. There are different quantum mechanical rules, like spin rules, and the change in spin rule, change in the angular momentum rule. There are certain rules, we call those as selection rules in the spectroscopy. Basically, we don't have that discussion in 10+2 level. So this charge transfer spectra are basically allowed by all these selection rules, and that's the reason when we say these kind of complexes being formed, they are intensely colored, because they are not forbidden, unlike a number of other spectra which can otherwise be taking place. Mn2 plus is such an example. We can take the discussion some other time maybe. So charge transfer spectra, whenever they are taking place, these are going to be all intensely colored complexes. And the reason for all these being intensely colored complexes is that these are very much allowed by all the factors. There is no quantum mechanical restrictions coming over here. Fine. So the two types of colors what we talked about. One is ligand to metal. Here, what is happening when we are saying ligand to metal kind of transition. So these kind of transitions are where electrons are present in the orbitals which are having the contribution like ligand. These are the transfers which are having the contribution. These orbitals, which when HOMO orbital is looking more like the ligand, and this is being excited to some orbital which is looking more like metal. You can see that where we have written as LMCT, the electrons are going into the empty orbital of the metal. LMCT, when we have written, electrons are going from ligand to metal. That is what we are saying. LMCT is ligand to metal charge transfer. So EG orbitals electrons are basically going into from the ligand. They can be going from the sigma orbital of the ligand, a molecular orbital, or the pi molecular orbital of the ligand. That is going to be possible. The second thing, second kind of transfer is metal to ligand. So when these electrons are going to be exciting from the orbitals of the ligands, like these orbitals or these orbitals, and basically when they are going to ligand's empty orbital over here, this pi star is the for ligand. When these electrons are going to the ligand's orbital, this is called as metal to ligand charge transfer. So these are the different possibilities: metal to ligand, ligand to metal. Although there are certain other possibilities like metal to metal that happens in potassium ferrocyanide. We can take the discussion some other time, maybe. Okay, so the question was about K2Cr2O7 and KMnO4. This compound K2Cr2O7 is having that orange color, and that color is originating from ligand to metal charge transfer. So oxide electrons are being transferred into the chromium's EG set of orbitals. That is how this charge transfer is going to take place. Similar thing happens in the KMnO4, where also this is going to be ligand to metal charge transfer case. We have got another case which is the other way around, the metal to ligand, and this is usually when the metals are the ligands are having empty pi star molecular orbital. We understand in oxide ion in K2Cr2O7 and KMnO4, as well as we can think about that can be the case with the K2CrO4. There oxide ions don't have a pi star molecular orbital, so metal to ligand kind of transitions are not possible, and in fact their metals are also in very much high oxidation state that electronic excitation can be quite difficult. Over here, thiocyanate ion is having empty pi star molecular orbital where electrons can be going from the ferric ions. So that is ferric thiocyanate where we are having the metal to ligand charge transfer possible. So in the question what we have had in these two compounds, what kind of charge transitions are possible, and the answer was that was charge transfer is taking place in both of these cases, right? Fine. Moving on, we have here next question. This was about the P block, basically oxoacids or halogens, and we were asked about the stability of these different complexes, these different oxoacids. And the actual question is which of these are undergoing disproportionation. We have learned about disproportionation. This is going to be a kind of a redox change where same element is undergoing oxidation and reduction. So what we are asked, which cannot undergo disproportionation. We understand disproportionation, and the answer is going to be 1 and 4. We understand that disproportionation is going to take place when some element is in intermediate oxidation state. And the same species, when this is undergoing oxidation as well as reduction, this is only and only possible when we have got the intermediate oxidation state, so that this can go backward and forward, like lower oxidation state it can go into, and at the same time it can be going into higher oxidation state. That happening, we can have disproportionation possible, right? If we have something which is lying on one of the extreme, like something is having the highest oxidation state or something is having the lowest oxidation state, then it is not possible. So we have said in intermediate oxidation state, disproportionation would be possible. But if something is in the lowest oxidation state, no further reduction will be possible. Something is in the highest oxidation state, no further oxidation will be possible. So in these cases, when we have got the lowest oxidation state like HCl, when we have got highest oxidation state like HClO4, that is +7 oxidation state over there, it was -1 oxidation state. That is the limit of the oxidation numbers of chlorine. We cannot go beyond +7, we cannot go beyond -1. So these two compounds are not undergoing disproportionation. HCl can undergo only and only oxidation, HClO4 can undergo only and only reduction. The other species which will be lying in between, they can be undergoing both the possibilities, right? We have basically one reasoning for these, which can be coming from the electrochemistry. Basically, we have got some simplified diagrams. Although we do not remember those diagrams all the time, but those diagrams we can be very much handy to understand, like in which case this disproportionation will be happening or which case it will not be. And this all idea is basically about the value of the delta G. And when we are plotting delta G versus F, basically we are seeing this change with respect to per Faraday of the charge. What is the change in what is the free energy change? So wherever this free energy change is going to be more and more negative, those kinds of transitions are going to be possible. So we'll be seeing for the nearby species how this curves can be related. We have got oxidation number. This is curve for the manganese, what we are seeing over here right now. We call this as Frost diagram for manganese aquascience. Manganese has got +7 to 0 oxidation state. This is we have got the values for the delta G that can be related in electrochemistry from their E0 values. So in this Frost diagram, when we are plotting delta G by F curve versus oxidation number, this kind of curve we are getting. Now, how we interpret this curve, how this curve help us understand where disproportionation will take place and which species disproportionation might not be taking place, even though this is lying in the intermediate oxidation state. So you see, what we need to do is we need to try connecting the neighboring points. And if we are trying to do so, the points which are lying above the curve, like this point for +6 oxidation state and this point for +3 oxidation state for manganese, they are lying above their neighbors when we are plotting these straight lines. This straight line we have plotted, this +3 oxidation state is lying higher. This straight line we have plotted, +6 oxidation state is lying higher. What does this tell us? This is telling us that +3 and +6 oxidation states will not be very much stable because they are lying on the more positive side of delta G. They can be stabilizing, like if you have got some oxidation state over here, if this is going on the lower side, either onto this side or onto that side, that can be decreasing its free energy. And that is why the species which are lying onto the higher side in comparison to that neighboring atom, the line connecting the neighboring atoms, those are going to be relatively unstable. So those maxima, we can say the local maxima which are present in nearby atoms, they are bound to undergo disproportionation. But if we are getting somewhere a minima, like we are getting here at manganese 2+, this is going to be stable, and we have understood, we have learned in a number of reactions earlier, manganese 2+ does not undergo disproportionation. It is very much stable, and it can actually be oxidized further, but this does not undergo disproportionation into say +1 or +3 or +1 or +4. It doesn't happen on its own. We may need to put some oxidizing agent to oxidize it or some reducing agent to reduce it back into the 0 oxidation state. But disproportionation for +2 is not known to happen. So that's the thing, how Frost diagram, although we don't have Frost diagram as such in 10+2 syllabus, this can help us understand if we have the delta E values, we can E0 values, using that we can plot the delta G curves, and these are used to predict the stability of the aqueous species in acidic or basic medium. Here is the diagram for chlorine. This is the basically Frost diagram for chlorine. This one is going to be in acidic medium. This one is an acidic medium. That is at nearly pH equal to 0, and this one is in basic medium, and this is for pH nearly 14. So what is happening? We can see here this chloride ion is lying over here. We cannot have the possibility of disproportionation. For ClO4 also we don't have possibility of disproportionation. But one interesting thing from here we can see that if you have got ClO2, this thing in basic medium, this is not going to survive, because if you join these lines, this is lying above, this is forming the part of local minima. This is not going to be stable. And if you go in the acidic medium, say for example, this time ClO2 is lying onto the local minima. This can be stabilized. So the same species ClO2 can be having different consequences when you are having acidic medium or basic medium. This is a wonderful application of the Frost diagrams. Although we might not have seen this Frost diagram in our usual discussion, this is how things go. This is how this Frost diagrams can be explained. Okay. The next example we are going to have is about the coordination compounds, and we have here the case of stereoisomerism in the octahedral complexes. So we are asked which of these compounds is having maximum number of isomers possible and oxalate the bidentate ligand they have given. The maximum number of isomers we are counting for the geometrical and optical both basically. So what is going to be our idea of thinking where the maximum number of isomers are possible? We are going to talk about where are geometrical isomer possible, and D is the compound where only geometrical isomer possible, and there is only optical isomer possible. That's compound number A. In compound number B and C, both the geometrical and optical isomers are possible, and we'll see when we're writing all the possible stereoisomers how the total number is going to change. We'll see here. So what is happening? First of all, we have this tris oxalato cobaltate. We are saying this is AA3 type of complex, and here we have got one pair of enantiomer. Total 2 isomers are possible. Here, many students actually have a confusion. They believe this compound is going to be symmetric because all the ligands are same, that this is AA ligand. So for oxalate, I'll be writing it like this, which is basically oxalate. There will be oxygen, one oxygen will be there, one oxygen will be here, that will be bonding, and we can maybe write ones here. Over here, there will be one C double bond O, there will be one here C double bond O. This whole thing will be writing later as this thing. Okay, this C2O4 2 minus will be writing like this. So this is one oxalate present here, another oxalate will be present here, another oxalate will be present here. This is first enantiomer. The second enantiomer, its mirror image over there is going to look like this. Now these two compounds do not superimpose one another. The reason why they do not superimpose is when we try to rotate this molecule by 180 degree horizontally, so that this right side oxalate bridge is going to be present over there. Maybe we can write this once as we have been writing the first one, oxygen, oxygen, double bond O, double bond O. So in order to match the oxalates onto the left side, when we are flipping this molecule by 180 degrees horizontally, then what will happen? This bridge, oxalate bridge, which was going below the plane, this we should say top backwards right side. Top to right backward side, which this bond was going to be, when we are rotating this molecule like 180 degrees, something like that, then this bridge, maybe I should label this in the green color. This green thing, when we'll be rotating this by 180 degrees, it would be looking like, maybe I should draw it once for the sake of clarity. Better I should draw it here, there will be writing something else. So we are rotating like that, and the rotated molecule I'll be drawing over here. This molecule, when this is rotated by 180 degrees, so what is going to happen? After rotation, this oxalate is going to be present here. The right side oxalate which was there, it is going to be appearing onto the left hand side, and that green bond which was going to be from top to backward right side, where that will be, that we need to understand. That bond by rotation by 180 degree will be now appearing here, front top to front right side. Here this is going to appear, and the another bond, let us put it this way. Sorry, not that bond, my mistake. I was trying to rotate the right molecule. So this particular bond, which was left top, this is going to rotate into the right front. Like backward left side is going to be front right side. And this blue linkage, what is present in the second molecule, which is from bottom to front left, this is going to be from from bottom to rear back. This kind of relation. This is going to be backwards basically. This green bond is going to be front side, something like that. So if you try to see, this is molecule number 1 and this is molecule number 2, this is molecule number 2 dash, this is the same representation as molecule number 2. If you try to superimpose the green parts, like this was the initial compound, that was the mirror image, this was the initial compound, that was the mirror image. Now these things do not match with this compound number 2. That is why this compound is going to have pair of enantiomers possible. This is very common confusion. Students believe this is AA thrice, everything is similar, so they should be symmetric. This is not. If you observe correctly, the left and right, they are mirror images, but they do not superimpose. How they are not superimposing? You can think of rotating. We have done here this, we have rotated by 180 degrees, and then we are trying to superimposing 1 and 2 dash. They are not superimposing. That is how we are going to compare that the compound number 1 and 2 are enantiomers. Okay, this compound is going to be relatively easier, quite straightforward. We are having two geometrical isomers, like both the AB, that is Cl and bromine, can be cis or trans to each other. So in this very first compound, we'll draw that oxalate. Oxalate, we can think, basically the oxalate can be present like trans to each other, something like that. They can be present. So here there is going to be one Cl and one Br, and there can be one possibility where these going to be cis to each other. So like Cl and Br are going to be in cis position. Now the second molecule, what we have written, this is not going to be symmetric. There is going to be optical activity associated with this. So when you draw its optical, the second compound, which is cis, this is going to be chiral. Its enantiomer is going to look like this. Here is going to be Cl, here it is going to be Br. So here we are having a total of 3 isomers possible, right? The next compound, we have got one oxalate and 2 Cl and 2 Br. Here we can be having 3 geometrical isomers, and out of those 3, the one which is all cis, that one is going to be optically active. That's going to be chiral. Total 4 isomers will be possible here. So the very first one we are writing, we can write here there is oxalate, and let us say here Cl and Cl are trans. So Br are going to be this. This is going to be symmetric. You can cut from the plane of the oxalate ring. So Cl on the top, Cl on the bottom, right? The next one, rather than keeping Cl on the transpositions, we can keep Br on the transpositions like this. This is also from that oxalate kind of ring. We can cut this molecule horizontally. Br on the top, Br on the bottom is going to be plane of symmetry. This is again going to be achiral. But when we keep both of these as cis, oxalate was present here. Let us say keep chlorine here and keep bromine here, this way. This is having no plane of symmetry possible. You try cutting from that same oxalate plane, and that top side you have got chlorine, bottom side you have got bromine. That's not going to be a plane of symmetry. Like we are thinking of basically this plane. If you are cutting from this particular plane, this is not going to plane of symmetry. This is not a plane of symmetry because here you have got chlorine, here you have got bromine. This is not a plane of symmetry because here you have got oxalate, here you have got Cl and Br. Okay, so this compound, when this is having no planes of symmetry, this is going to be having its non-superimposable mirror image. For that, this is going to be Cl, Br, there is Cl, and there is one Br. So this compound is going to have a total of 4 isomers possible, right? That is the maximum number of isomers for all the given. We have got one more example actually. This is COCl3, ClBr3. And in this case, we have got the 2 possibilities. We have here, this is Ma3B3 type of compound. We have got 2 geometrical isomers. One is facial and one is meridional. So only 2 isomers are possible here. We can draw those. So we can say we have got chlorine here, chlorine here, chlorine here, bromine, bromine, and bromine. This is going to be what we call as facial isomer because the 3 chlorines are going to form one face of this octahedron, or you can say the 3 bromines also are going to form another face of a tetrahedron, sorry, octahedron. That is what we call as the facial isomer. The next one is going to be meridional, where one of the chlorines, if you are moving away from this top position or bottom position to somewhere like this is going to be your meridional isomer. So here the another bromine is going to be present here, and that bromine is here. Now these three chlorines or three Brs are not present on the, none of these can be present on the basically any of the phases possible. That is how we were having these different kind of isomers possible. So going back to our initial question, the answer we could see was this thing, where we have seen 4 isomers possible, right? Okay, going to the next question. Here we are being asked about which of the following is not a Lewis acid-base reaction. What we understand in Lewis acid-base reaction, there is a sharing of electron. One is electron donor and another is electron acceptor. Please note, when we are saying Lewis acid-base relationship, although there are electron donors, there are electron acceptors, there would be some compounds which are electron donors, there will be some compounds which are electron acceptors, but this is never a transfer of electrons. Like electrons are not completely transferred, what we are assuming here. So basically this is going to be a non-redox change. Whenever we are having Lewis acid-base reaction, this is going to be essentially a non-redox process if it is a Lewis acid-base reaction. So here we can very easily possibly identify where this is not happening, because zinc is converting into zinc 2 plus. That is going to be a reduction that cannot be the Lewis acid-base reaction. We'll see a little bit discussion about how this iodide can be converting, triiodide can be converting into I5 and all. So electron donor acceptor, no electron transfer involved. That is what was supposed to be our idea. And if this is a redox change taking place, like here, what we see here, zinc converting into zinc 2 plus, this is going to be loss of 2 electrons. This is going to be oxidation. So oxidation cannot be a Lewis acid-base reaction. Okay. Transfer should not be involved, then only it can be acid-base reaction. So here we will see basically what is going to be electron donor atom and what is going to be the electron acceptor atom. So this is the first example. This is going to basically the correct answer. This is going to be basically a reduction. This is not an acid base. In all other cases, we'll be seeing these are acid base changes. So the second option was I3 minus ion as sharing its electron pair with I2. I2 has got quite basic properties. We have seen couple of examples. Iodine is very easily behaving as electron acceptor. There are low line d orbitals available where electrons can be very easily accepted. And this is going to be Lewis acid-base reaction. We'll be seeing its structure in a bit. That's why we have put a star mark over there. Chloride sharing its electron pair with this COCl, that is converting into COCl2. That's deep blue color complex. So this is cobalt. We can say this is one chlorine, this is another chlorine. These 3 chlorines were present. There is COCl3 compound, and if there is one chloride ion present, that can be sharing its electron. That is how our tetrachloride deep blue color complex is being formed. Characteristic compound for the cobalt, it's having deep blue color. And hydrogen, water can be sharing its electron in SO3 to convert into that sulfuric acid. That's very popular reaction. We have seen integration of sulfuric acid. So this is what was happening in this acid-base kind of Lewis acid-base reaction which was taking place. Oxygen was the electron donor basically here. This one was the Lewis base, SO3 was acid. Here chloride is the Lewis base, COCl3 is the acid. And in I3 and I2 we'll be seeing here in our discussion how that is happening. And we'll go a little bit one step backward where we have seen the formation of triiodide. So basically I2 reacting with iodide ion is converting into triiodide. This is what we call as I3 minus ion, which is going to be sp3 dehybridized, and this is going to be linear molecule. This bond angle is exactly 180 degrees. Okay. And when we have got one more iodine coming onto this is I3 minus ion, one more I2 molecule is joining in. Then this iodine basically, which was having here this iodine on the right side, this was having the negative charge, this was having high electron density. This can be sharing its electron density into empty d orbital of this one of the iodine. And that is how this kind of complex formation is taking place. This is the Lewis representation. So 5 iodines are present here, and these are not actually linear. The actual structure of this compound is going to be like this. Here, the central iodine, this is the central iodine atom. This is going to have total of the 4 bond systems present, because we can think this was one of the coordinate bond found by 2 of the lone pairs. This was one of the coordinate bond found by 2 of the lone pairs. So 2 of the lone pairs are being consumed. This one lone pair is remaining, another lone pair is remaining. So the steric number of this compound was going to be 4. With steric number 4, we have got sp3 hybridization, and because there is 2 lone pairs, the structure is going to be bent. So I have written here I2. This I2 is going to basically linear, so this is going to be quite long bent molecule with 3 atoms in one line, 3 atoms in a line, and iodine in the center, something like this. Okay, so here now this bond angle is going to be a little bit changing from 180 degree. Earlier it was 180 degree because of those electronic repulsion. It could be changing. This central iodine is having 1 lone pair present over here, and this iodine is having another lone pair over here. That would be responsible for the little bit more repulsion from this side, and this bond angle is decreasing. This bond angle is also decreasing, and this sp3 hybridized bond angle of the central iodine is going to change from 100 and like usual the regular angle 109. This is changing to nearly 95. Quite decrease is happening with respect to the tetrahedral, that usual bond angle. Okay, that was our question on the Lewis acid base, where we could see there was no implication of the chemical bonding coming as well. Chemical bonding is actually something which will be having implication in almost everywhere in the inorganic chemistry and many places in the organic chemistry as well. Fair enough. Moving on to next example. The next question we are having is on the ionic equilibrium, that is acid-base reactions. And here, this is pretty straightforward question. We are being asked about the solubility. So we understand the acidic compounds and basic compounds, how their solubilities used to be. So we can say carbon dioxide is going to be soluble in the sodium hydroxide base. Sodium hydroxide is going to be soluble in the acid, that is HCl, and zinc oxide is going to be soluble in the both, that is amphoteric thing. Basically here all these things given to us were amphoteric in nature, so all of these would have been soluble, but we need to see the other possibilities. Here these 3 compounds would have been soluble, so this option number C would also have been correct if this was a multiple answer, but the thing is they have said here oxide B is soluble in HCl. This oxide number B will be soluble in HCl as well as NaOH. So on the basis of that, we can be excluding this option number C. Otherwise, option number C could also have been possible. Choosing single option, will be going with the option number B only. So here is our reasoning why we do so. Anything which is soluble in sodium hydroxide is expected to be having either acidic nature or amphoteric nature, and anything which is going to be soluble in HCl, on the other hand, will be something which is having basic nature or the amphoteric nature. And if something is soluble in both, it would imply that this thing is going to be amphoteric in nature, as simple as that. So we know their natures and we have had discussion, so we'll be going with the option number B. Here are the compounds which are, when they are hydrolyzed, what they are basically converting into. So if you are trying to dissolve these compounds into aqueous sodium hydroxide, the product what we can be expecting, the product would be like carbon dioxide is converting to sodium carbonate, sulfur dioxide, sodium sulfide, ZNO is converting into sodium zincate, and SNO2, sodium stannate, and just like lead dioxide is converting into sodium plumbate. HCl if you are using, then these compounds what we have seen, they can be dissolving. We can be getting in different cases these compounds, and although in this case we have written PbCl4 is being formed, PbCl4 in aqueous medium is known to undergo hydrolysis, and this converts into PbO2, which is black colored insoluble compound. And same thing is actually known to happen with SnCl4. This compound is also an aqueous medium, undergoes hydrolysis, and that is supposed to be converting into H2SnO3. that is tannic acid. That kind of compounds can ultimately be formed. Initially, they can be dissolving NaCl, forming PbCl4 and SnCl2. These compounds will not be certain Cl2 up to certain extent can be following the same thing. Hydrolysis is going to be relatively slower, but PbCl4 and SnCl4 are definitely undergoing hydrolysis to give you those kind of products. So we'll be sticking to the option number B, where carbon dioxide will be choosing soluble in NaOH, Na2O soluble in the HCl, and ZNO soluble in both acid as well as base. Those were all the questions in this inorganic sections, and we'll be now moving to the physical chemistry section, the paper 1 only. That's all for now. Thank you. Bye bye. Take care.